Hi everyone and welcome back to a new video about controller design, and we continue with the subject of Root Locus method, and this is our example number 9. In this example I will discuss the design of a LagLead controller. So we have discussed the lag controller and the lead controller separately, and this is the combination of these two controllers. We will of course use the calculations, and we will work it out step by step, and we will verify our calculation using simulations in MATLAB. So let's look at our example number 9 about the lead lag controller design of a second order system in this case. So we have the following diagram given. The controller, which is in cascade with a plan and a unity gain feedback configuration, input R, output is Y. This is the plan, GP, which is 1 over S times S plus 7. So we have a pole at the origin and also pole at minus 7. The controller, the LagLead controller, is given by this expression, which has a gain K and the lead associated part and also the lag associated part. So you can see the Z and the P, so the 0 and the pole of the lead, and also the 0 and the pole of the lag. So we have actually in this case 5 parameters, and we will determine that step by step using the given design specifications. And these are the following. We have an overshoot must be less than 20%, 0.20 for MP. The settling time with the 2% criterion must be reduced by a factor of 2 compared to the P-controlled system. What does it mean? Actually the following. You have your settling time of your LagLead controller, your LagLead control system at the end of the design, and it must be a half of your settling time using the proportional controlled system. So that's what we need to do. For the third one, the third specification is the steady state error for ramp input. It means actually the velocity error must be reduced by a factor of 10 compared again to the P control system. And that means the following. Your velocity error of the LagLead control system must be 10 times smaller than the velocity error of your proportional controlled system. And that will be worked out step by step in the following analysis. So let's look at our solutions. How we do start? We start with the given specifications. I start first with the overshoot. From there I will work towards the design point we will need for our determination of these parameters of the LagLead controller. So step 1, determine the design point. From the 20% overshoot specification, I can go to the damping ratio using this formula, and that will give me 0.456 for my zeta. Now, using the pole of the origin and the pole at the minus 7 for the open loop system, the plant, I can determine the real part of my P-controlled system. That's actually how we start, and that's actually just the average of these two poles. So we have a pole at the origin, 0, we have a pole at the minus 7, pole 1 and pole 2, and you take the average, that will be minus 3.5. This is our real value of our design point. In this case, I can already calculate what the settling time will be for the P-control system. That will be 4 over this absolute damping, sigma of D, that will be 4 over 3.5, will be 8 over 7, exactly, that will be approximately 1.14 seconds. And that will be, of course, verified in the simulations. The imaginary part, in this case, is then using geometry, sigma of the absolute value times the tangent of our cosine zeta. So omega d damped radian frequency, again 3.5, you take the absolute value of the absolute damping, tangent of the arc cosine of your zeta, which is already calculated, and you will get very close to 6.8. That is your imaginary part. So if you collect these values, you can determine your dominant closed loop poles, which will then determine the dynamics of this system. So we will then use the sigma of D and the omega D, which will then give minus 3.5 plus or minus J 6.8 for the dominant closed loop poles. For the design point, I will just take one of these close to poles, so I will take the one with the positive imaginary part, which is actually shown here. So this S1 is my design point, and in the figure on the right side you can see that there is a pole at the origin, also at the -7, which is actually the planned poles, and we have our design point S1, which is given by the real part of -3.5 and an imaginary part of 6.8, J6.8. So we will now continue with the analysis, the step 2 of the P-controlled system, and then we will determine what the performance of that system is. So let's look at it first, the P-controlled system. That means the G, the proportional control, is just a K. So we will just assume that it's a K, and we will see what we can achieve using the proportional controller. So the root locus equation is of course given by 1 plus the loop transfer function is equal to 0. Now the loop gain or loop transfer function is in this case given by the proportional controller times the planned, which is then given K times the planned, and in simplified form is this expression. Then we have, if I have this one, I can substitute in this expression, which is then shown here. Now, if I now place the one on the right hand side, I will get a minus sign. It will be just this expression, loop transfer function, will be -1. And this is then, even simplified, just isolating the value of the K, will be this. I need to evaluate the value of this K, which is the controller gain, at the design point, which was the given S1. So I will substitute for S1 this value for S, and I have done this expression. So if you now substitute it in detail, you will get the following expression, and if you simplify this, you will have this expression. Now if I now calculate, of course, the magnitude, the absolute value of this, the P-controller gain, K, I will have the following expression, and if you do the math with the square root of the squares of the imaginary and real parts for each term here in the absolute sign, you will get very close to 58.5 for the value of K, and that means that we require a P-controller with a gain of 58.8 in this design. For this design specification, that means we have the proportional controller gain determined. So let's look at the velocity error for this P-control system then. So EV proportional controlled, that means 1 over the proportional controller velocity error constant. So that is actually the KV. So this is actually our velocity error constant for the P-control system. That is determined by using this formula, limit of S approaching 0 of S times your loop transfer function. A loop transfer function L of S was given here, so I can just substitute in this, and you can see that the S in the expression and the S in the denominator of the loop transfer function will cancel each other out. So I can then see this already here, and if I just substitute also the value of K here and also approach that to 0 for S, I have then in the next step the following. So I get then the value for my velocity error constant for the P-control system, which is then very close to 8.36. If I now want to calculate what the error is, in this case for the P-control system, that will be 1 over this value will be 0.1196. That's actually your error for your P-control system. Again, this is your velocity error of the P-control system. Now, what does it really mean? We have also discussed this in the LagController in particular with the previous examples. This means the following. If you have an input, and it's applied, for example, unit step input, unit ramp input in this case, this is actually the expression. So RT is equal to the linear increasing formula with the step input expression multiplied. That means actually it starts at the origin. Then the value in the unit step response, the unit ramp response, will be the following. So you have the output is equal to the input, which is the unit ramp input, minus the error what we have calculated. So if you look at it, for example, at time equals to 2 seconds, that means actually at 2 times equal to 2 seconds, the value of this one will be also 2, which is of course because this is just a linear formula with a slope of 1. So if you have here, for example, 25, it will be also 25 in value. Then the output will be settled, and we have then the output at this value for 2 seconds. So if I just look at y at 2 seconds and also at the unit ramp input, then we have the following situation. It will be then 2 minus the error we have calculated, and it will be then this value. So this is actually the value which you will read from your plot in the simulation if you do the unit ramp response. And this is again our output at t1 is equal to 2 seconds for the P control system. So let's look at the next step, because we have now determined our P control system performance and also the value of the P controller gain. The next step is actually calculating the lead controller. So what we want, of course, is achieve a 2 times decrease in the settling time, because that was one of the specifications, also the overshoot, of course, and we need to, of course, also reduce the velocity error by a factor of 10. For speed purposes, we need to look at the LagController design, so for the settling time reduction, also for the overshoot. For that, you start actually and use actually your LagController. The LagControl will not do much for increasing your speed of your system, so that's actually why we start with the LagController, and then afterwards we will look at the LagController specifically for our velocity error performance in the example. So the LagControl will be done after this. The LagController is given by this expression. You can see that I have taken the K of the total controller LagLead in this expression, so I will use that also after this analysis. You can see again the 0 of the lead and also the pole of the LagController. The settling time must be decreased by a factor of 2, as said before. That means the following: the settling time with this LagController, what I have to achieve is the proportional controller settling time over 2. That means 1.14 we had in the proportional controller case. I divide it by 2 and I have then 0.57 seconds. So this is what I really need to get after the unit step response. That means the following: using this new settling time, my new absolute damping value of the sigma d lead must be then this value. So it is like 4 over this new settling time for this lead control system will be 4 over that 0.57 will be then 7 radians per second. So this is actually what I really need to have. It's approximately 7 radians per second for sigma d with the LagController design. So this is the real value of the new design point. Now again, the new damped radian frequency, so the frequency omega d lead, must be also calculated and must be placed at, using geometry, the sigma d lead, and then times the tangent of r cosine of that zeta. Now the zeta is again the similar value, exact same value as before, and this is just 7. So if you just substitute the values, you will get here 13.6, and this is then our imaginary value of the new design point. So the new design point, I just call it S1 star, just designate it as a new design point, will be then given by this expression, and I have then now the sigma d with the lead one and omega d with the LagController, and I have then this expression will be then minus 7 plus j 30.6. So the root locus equation is then given by this expression again. We will use that also here, and then where the loop now transfer function will now be given by the lead transfer function, LagController, and also the plant, which is shown here. And this is the lead transfer function with the plant in a simplified form for our loop transfer function L of S. Then we have the following. I can say then 1 plus the loop transfer function for this case will be 0, and that will be used now in our analysis for the angle criterion, because I want to calculate, of course, the K and also the Z lead and also the P lead. Before I move to the angle criterion, let's look at this plot, the sketch in more detail. What I see also again the 0 and the minus 7, the 2 poles of our plant. The The initially used design point is shown here as S1, which is a green dot here, which is actually with the minus 3.5 the real value and the 6.8 is the imaginary value. The new design point is at minus 7 J 13.6, which is actually shown here, so which is actually that red dot. You can see that this pole at the origin will have the same phase contribution as for the S1, but this pole, which has this phase contribution, actually this one, will now have a much different phase contribution, which is actually in this case 90 degrees. And that will of course be determined shortly, step by step, and we will then use also the magnitude criterion to determine what the length of these two lines are, and also the associated with the zeros and the poles of the LagLead controller, such that the root locus equation is satisfied. So let's look at our angle criterion. What you see is the phi 1 and the phi 2 and also the phi lead must be used in this expression, and that is the phi 1 is the associated phase contribution of this pole. Phi 2 is the associated phase contribution of this pole actually, so this minus 7 is actually this, and the phi lead is actually what you really need to add using the lead controller, such that this is minus 180 degrees, which is one of the criteria of our root locus equation. So the phi 1 is the phase contribution again at s is equal to 0, the other one at s equal to minus 7. So phi lead is then the phi of the 0 of the lead controller minus the phi, the phase contribution of the lead controller pole. So that's what's also shown here. Now, I have many unknowns in my transfer function of the lead and also the lag controller. So I really need to select some values because I have 5 unknowns and I have actually not 5 unique equations. I really need to take some values in my unknown. So I will select, for this example, we will select the lead control 0 at s is equal to minus 3. You might say why you choose minus 3, not minus 4, or minus maybe 10, or maybe 0. That's also possible. If you place your 0 too close to your origin, that will of course have some effect, but it will maybe cause the dominant close poles not be dominant anymore. And if you place it too far, then the 0 will have very minimum effect on the speed of your system. So I have just taken that around in the middle of this design and also at the origin, which is actually approximately at minus 3. You can of course try also with minus 4, but will maybe also do the job. So I have just taken minus 3. So Z lead will be 3 in our expression for the lead controller. Okay. So again, this is the minus 3, and this is the 0 I have just placed, and this is the Z lead of my lead controller, and this is actually the magnitude contribution and also the phase contribution of this Z lead. We will determine that shortly. Then we have the following. The lead controller here is then given by K times the S plus 3, which is then the 0, divided by S plus the P lead, which will be the pole of the lead controller, and this will be determined, and then this will be also calculated. So this is actually what we really need to do in the next step using magnitude criterion for the lead control system. So again, looking at the angle criterion in more detail, this is the plot which is now shown in a larger view. What you see is the two poles again of the planned 0 and minus 7. You can see the phase contribution phi 1 and phi 2. You can see the 0 at minus 3, which was selected, and that's the phi z of lead. You can also see the pole, which is already given in a value, but we will calculate this, and you can see that this has also its phase contribution. So again, the angle criterion, we have seen this before, and we have then selected was minus 3, so again this was the lead controller. If I look at phi 1, this angle, I can calculate that easily by looking at the half angle, which is 180 degrees, minus this angle, which is actually this analysis, and you will have 117 degrees for this one. The same is actually for this one, but this is actually a right angle, so this is actually very easy to calculate. It will be 90 degrees in this case. For the Z-lead, for this one is similar action, so you will have 180 degrees minus this angle, which is calculated by arctangent of the height, 13.6, divided by this distance, which is 7 minus 3, which will be 106 degrees. So from the angle criterion we get the following. The phi lead must be then, which is actually this expression rewritten in different form. Phi lead is equal to minus 180 degrees plus phi 1 plus phi 2. So that means phi lead, the lead controller, must contribute in total plus 27 degrees for this design. I know my lead controller phase, which is then the action of the lead 0 and the lead pole. So lead 0 will have a positive phase contribution, the lead pole will have a negative phase contribution. That's actually the expression for the lead phase contribution. I know the expression, the value for my lead 0 phase, which is 106. I also know the lead phase contribution in total, which is 27 degrees. So if I now do the math here, just substitute the values, I know then what the phase must be for my lead controller pole, which is now 79 degrees, which is actually this angle. Now, if I know the angle here, and I have the geometry here, I can now calculate using tangent this value of the pole, which is actually the tangent of this pole, I mean the phase, is equal to this height divided by this distance, which is actually shown here. So this is still unknown, so he will now come to that 9.6. So if you do the math here, just substitute the value of the phase, and you will then, you have only one unknown, you will get then the pole of the lead controller, which is then given by this expression, which will be 9.6. Then the lead controller is then given by this expression, still the S plus 3 as selected. Now we have determined also the pole, S plus 9.6, but the K, which is the lead controller gain, is still unknown, and that will be determined now in the next step using magnitude criterion. That is our next step. So let's look at the magnitude criterion. What we need is, of course, again using root locus equation, we can calculate K for this lead control system. This is again the root locus equation. As a reminder, we have this now, and only unknown is the K here. If I simplify this, just take the numerators and denominators together and a K also in the numerator, I can now say again the plus 1 here on the left hand side placed on the right hand side, and this must be of course isolated for K, so it will be isolated. You will isolate the K and you will have this expression, so you will actually work out this, which is I think very straightforward. Now if I now want to evaluate this or calculate this K for the lead controller, I need to evaluate it at the design point, which is of course the new design point S1 star, which is minus 7 plus J 30.6. Then I have the following. I just substitute the value of S1 star in this S in 4 places here, and I will now do the math. You will have then this. If you just substitute and simplify this in the next step, you will get the following expression. And if you now want to take the actual value, so absolute value, you will need to take the absolute value of this one, absolute value of that one, and then multiply that by with each other. For the numerator and denominator, exact same procedure, and you will get very close to 203 for the K. So I know the lead controller gain now, which is 203. The conclusion for this one is that the lead controller, specifically only lead controller, is now given by this expression. The gain is now calculated, the 0 was selected, and also the pole is calculated, and we have now our lead control transfer function. So let's look at their next step. We have now determined the lead controller. The next step is the LagController. The LagController design is actually adding the LagController to the designed lead controller. The step 4 is the LagController design. So I know from the specification that we require a 10-fold decrease in the velocity error compared to the P control system. So the steady state error problems, design questions will be tackled with LagController Design. And also, if you want to, of course, completely eliminate your steady state error, you will use the integration or PI controller. So in this case, I know that the velocity error of my LagLead controller at the end must be 10 times smaller than my velocity error of my proportional controlled velocity error, which was calculated already. It was 0.1196 divided by 10, and this is what I really need to see in my final result for my velocity error for the LagLead controlled system. Now, from this condition, I then can calculate what the value of the velocity error constant must be, which is again the formula of the velocity error rewritten in different form, which is then 1 over this value, which will be then 83.6. That means the following: this constant must have a value of 83.6 in the final design of the LagLead controller. Now, this is the required value of the velocity error constant again at the end of the design. So lead controller action, we have done, of course, something with the lead controller in the previous step, step 3. So what have we gained so far with the lead controller? Because we have added some dynamic in the system that might already have changed the steady state error compared to the P controller. So let's look at it. So specifically the lead controlled velocity error constant was given by this expression. It can be written in this expression, and of course just specifically looking at the lead. And then we have then the following expression, of course just substitute the value for the lead control transfer function, also the planned, and you can see that if you just work out the s in the expression for the limit and also in the denominator, and you will substitute for the s is equal to 0, you will see that it will be 9.06. So the velocity error constant of this lead control system has already 9.06. Of course, I need to go all the way to 83.6, but I have actually a small increase in my velocity error constant, which is of course beneficial. So I can see here, with the lead controller alone, we have increased the velocity error constant from 8.36 to 9.06, which is not much, of course, but it is something. So there's a little bit improvement by only, of course, using lead controller. Of course, lead controller is not specifically used, that is not the purpose of the lead controller, to reduce your steady state error. That is actually done with the LagController. And again, the lead controller is primarily used for speed and also in overshoot specifications. So I need actually now not go all the way from 8.36 to 83.6, but I can now start at 9.06 and then move to the required value for the LagLead controller velocity error constant. So how we need this, and that means now the LagController action. As the next step, the LagController needs to improve now the velocity error from this 9.06 to 83.6, which is not the 8.36, but you start at 9.06 because that was already provided by your lead controller. So it is the lead controller that will help us a little bit by its own dynamics. So what we can do, and we know that from the LagController discussion in the previous separate videos about the LagController design, that the ratio which you need to improve here is also the ratio which you use for the 0 to pole ratio of your LagController. So the LagController 0 and a pole ratio, that is exact same as the required ratio. So ratio of the velocity error constants is the ratio of the 0 and the pole of the LagController. That means the Z lag over P lag is the value which you actually calculate here, which is the 9.23. So I can say my LagController 0 must be 9.23 times the LagController pole. Again, we need to make a choice, a reasonable choice for our design here for the pole or the zero. So I will just take the pole of the lag at minus 0.01. I purposely take it close to the origin such that the negative phase contribution of the lag is not that much. We have discussed this in more detail in the previous videos. If you take this, for example, 1, that is perfectly fine, mathematically correct, then the lag 0 will be at 9.23, and then the negative phase contribution will be too much, and it will be maybe unstable already. That is already, of course, a different problem, and maybe your dominant close to pulse approximation will not be valid anymore. So what I always do is I place the pole of the lag very close to origin, such that the distance between the zero of the lag and also the pole of the lag is not that much, but still the ratio is as shown here. That means the zero of the lag will be then at this location. Just do the math for yourself. Then the LagController controller is then given by this expression in general form, and if I now substitute the value, I will have this expression. What you see in the lag transfer function is that there is no k. That k, which is the k of the lead controller, will be also the gain of the LagLead controller. So the k, what we have already determined, 203, will be also used for the LagLead controller. Of course, if I do the math again here, you will see a slight change in the gain, but that calculation is not really necessary. If you, of course, want to be very accurate, you can do it for yourself. So next step is the final step, step 5, LagMidControl Design. We collect the lead controller and also the LagController designs together, and we have then our final controller. So lead controller was this expression. We have done this again with its gain 0 and a pole. Lag control we have just determined, which is given by this expression. If I now want to calculate the LagLead controller, which is just the cascade of these two expressions, I have then the following. This is of course worked out in more detail, and then we have this expression. Then the LagLead controller will be given by this expression, which is now has 2 poles and 2 zeros and its associated controller gain. So let's now look at our simulation results and verify that this is indeed what we have calculated and also what we have designed. We start first with the P controller, which has a value of 58.5, and we will look at the root locus plot and also unit step response. And after this, we will discuss the unit ramp response. So this is the unit step response on the right side, and also this is the root locus plot. You can see the design point here, or dominant poles there. I've circled that in green, and you can see on the right bottom what the location of these poles are, and also the damping ratio here. And in summary, if you see it in big picture here, you can see that there's a minus 3.5 plus J6.8, which is exactly what we had. And damping ratio is 0.458, which is a little bit larger than what we had. We had 0.456, which is of course very close to what we have used in our calculations. If you look at the unit step response, you can see that the settling time is 1.09, almost 1.1 seconds. We have calculated that the settling time was 1.14 seconds for the P control system, so that's actually also fine. The overshoot is 90.9%, which is less than 20%, so you can see that it's actually at the edge in our design. So in summary, we can say overshoot is less than 20% as required, and settling time is 1.09 seconds, which is less than 1.14 seconds as calculated in the P controller case. So that's all fine. Now let's also look at the unit ramp response for the same controller. What you see is the blue line is the unit ramp input, which is just a linear line. You can see at 0 it's 0, at 1 it's 1, at for example 2 it's 2, at 3 etc. it's increasing with the same slope of 1. This is unit ramp input, this is unit ramp response of the P control system. So the R and the response of that one is shown here in orange or red line. So what you see is I've just selected the location on the plot for each of them. So I have now taken at time is equal to 4 seconds. The ramp will have an x value of 4, which is the time, and also the y value of 4, which is of course trivial, which is a linear formula with a slope of 1. But the output at time equal to 4 will have a value which is 3.88034, which is just, of course, not 4, which has some error. That's actually what we call the velocity error. So if you now summarize the result here, you can see at time equal to 4 seconds, you can see that the unit ramp is just 4, but the output is 3.88034. So if you now calculate the error here from the simulation, you will have 0.11966. We had calculated it was 0.1196, so very close to what we have here. So that is a very nice result just looking at the P-controlled system. So let's then look at our LagLead controller design, and this is the first design we have initially what we have designed. Again, the gain, the zeros and all the poles of our LagLead controller. Again, the root locus plot and the unit step response. Root locus shown here with the design points, and also on the bottom you can see the current location of these design points and also the damping ratio. And in summary, it is shown here. Of course, we have changed our design point. We have, of course, moved the design point because of the specification. We have to increase the settling time. I mean, this decrease settling time by a factor of 2. That we have shifted actually the real part 2 times to the left. That is actually what we have here. We had here -7. It is -6.96, so it is very close to -7. And it is plus J13.6, which is exactly what we have. And damping ratio is exactly what we had also in our calculations. If I look at my unit step response, I see the following. The overshoot is fine, so it is 9.44, much smaller than what I actually have expected. But the settling time is a little bit larger, so it is 0.628. Of course, I need to have 0.57 max. So this is something we need to figure out, we need to tune. That's actually, this design is okay in terms of overshoot, but settling time is not that, not the value we have actually designed for. So we can tune this. This will be not that difficult. First we start with the tuning the gain, and we will see what will happen with other specifications. So let's look at also to the unit ramp response of this exact same lead control design. Since this is of course a lag controller in this controller, the response of the system is very slow. So don't look at your unit ramp response at, for example, 2 or 4 or 5 seconds, but look at it after maybe 100 seconds, maybe 200 seconds, if you want to make accurate measurement or determination. I have done it at 100 seconds, so actually the plot at the beginning is not shown here, so I have zoomed in actually at this point. You can see the ramp is at 100, at time is 100 seconds, it's equal to 100. But the response, which is this red-orange line, is at time equal to 100, 99.988. That means the following. At time equal to 100 seconds, unit ramp is 100, output is 99.988, the error is 0.012. And we had calculated it was 0.01196, which is very close to what we have now simulated. So the calculation and simulations are very close to each other. That is actually a very nice result. This means actually this controller, LagLead controller, will do the job in terms of steady state error, velocity error, but the unit step response showed that the overshoot was okay, but the settling time was a little bit larger. So we really need to tune this. So that's actually what we need to do now. So I have tuned this. I've changed the LagLead controller gain, increased it from 203 to 236. That's actually done in MATLAB, just using the tuning method tool. The rest of the parameters are the same. So we have again the root locus and the unit step response. Again, the location of the dominant close to poles are also shown here on the bottom right. The damping ratio also, and the summary here. You can see that the damping ratio is a little bit increased. So I expect that the overshoot also will be larger than the previous design. The design point here is also very close to what we have in the real part, but the imaginary part is also a little bit increased. So this is actually what we have now. If I now look at the unit step response, I can see that the settling time is exactly the edge, so 0.57. And I can see that this is okay. And the overshoot is now larger than actually the unit step response with the first LagLead controller, which is now 13.2. It's also okay because it is less than 20%. So in summary, it is less than 20% for the overshoot and also at the edge for our settling time. So this will definitely do the job in terms of the unit step performance. Now let's also look at the unit ramp response of this same controller. Again, the gain is increased from 203 to 236. You can see again I have checked that at 100 seconds because the system is a little bit slow due to this lag. I can see this at time equal to 100 seconds. The unit ramp has a value of 100. The output itself has a value of 99.9897. You can see that also in the MATLAB accurately. And if you just calculate the difference between the actual value, what we need to have, of course, because the blue line is the input and the orange line is the response, so we need to track the input, and this is the velocity error, then you will get the 0.0103. We had a maximum allowed error of 0.01196. That means this is smaller than what actually maximum allowed. So this is definitely better, has a better performance than the previously LagLead control design. And why is this the case? This is actually very simple to explain. We have the gain now increased from 203 to 236. So by increasing the gain, we have actually added more power in our system that of course increased the overshoot, but now also decrease the error. So by increasing your controller gain, you will increase the overshoot, which is of course not good. You will increase your speed, which is good, but you will also decrease your error, which is also good. So there are of course some optimum values for your gain, but if you of course want to increase that, for example, to 250, 270, you can do that. If you of course want to go all the way to the edge of your overshoot, then this will of course also decrease. But if this is okay, if this will do the job, then it's not really necessary to go all the way to the edge of the overshoot. But what you see is that this design is definitely very nice for our specifications. So let's look at the summary of the results in the simulations. This is the proportional controller with the specifications, overshoot, rise time, settling time, final value, the position error and the velocity error, and also the velocity error reduction ratio. This is the LagLead controller we have designed initially, and this is the LagLead controller we have then adjusted the tuned version. So you see the exact same actually for these two, only the gain is different. You can see that this has the specification we have discussed. You can see that this is a very small overshoot compared to this one. It is more than two times smaller. You can see also that the rise time is almost 2 times smaller because the gain is of course also much larger. You can see that the settling time is larger, so this was not what we wanted to have. And you can see that the velocity error reduction was almost 10. So this was according to specifications, but this settling time was not according to specifications. So this is not what we can use. Now, if I now look at this diagram, specification, the performance of this controller, I can see that the overshoot is 30.2%, which is less than 20%. The rise time is also smaller than that one. It is around 100 milliseconds. This is at the edge of the settling time maximum allowed value, and I can see that the reduction in the velocity error is now 11.62, which is of course more than 10. That means this controller and in this configuration and the unity gain feedback configuration will do the job, and this is the best choice in this case. Of course, again, if you want to adjust the zero, adjust the polar, adjust the gain, that is all possible. You have actually many ways to improve this, but that is actually a tuning operation, and that is of course possible if you have more time or more specific wishes for your system. But for this exercise number 9, for the LagLead control design, we have now determined our required transfer function of the LagLead controller. So that is now the final result. I hope this is also in combination with the lag and the lead clear for you how you can design a LagLead controller step by step. And if you have, of course, questions, comments about this, just please let me know about it and I will try to answer them as soon as possible. Thanks again for your time, and see you next time, and take care.